Hello and welcome to this lecture on information theory and coding technique. My name is Sumit Kumar Chaube and today I am going to discuss information capacity theorem. Okay, so information capacity theorem, it is also called Shannon and Hartley theorem. It tells us the maximum rate at which the information can be transmitted over a communication channel of a specified bandwidth in presence of noise. It is basically an application of channel coding theorem to a continuous time analog channel subjected to Gaussian noise. Okay, so you can see that here we are actually getting the theoretical tightest bound on the information data rate that can be communicated at an arbitrary low probability of error using the average received signal power S through an analog communication channel subjected to a wide Gaussian noise power n. So here C is our channel capacity in bits per second. This is equal to B times log base 2 1 plus S by n. Here B is the bandwidth of our communication channel, analog communication channel. S is the signal power and n is the noise power, and C is our basically channel capacity in bits per second. Okay, so here we are actually getting the theoretical bound on the communication rate of the information. So that is going to be our channel capacity. The maximum rate through which we can communicate without having any error will be called our channel capacity. Okay, so now we are going to see some of the problems that are based on this theorem. So very first theorem, this has also been asked in the university exam. Here we have a voice grid telephone channel which has a bandwidth of 3400 hertz. So here in this case B is given to be 3400 hertz. So this is we know. Okay, also we know that SNR in dB, so let me write it like this. So SNR in dB is equal to 30 dB. So you can write this 10 log S by n, and we will get here 30. So S by n will be equal to this is actually base 10 as well, so 3 10 to the power 3, which is equal to 1000, right? So this is the value that we got for the signal to noise ratio. Now we have to calculate the channel capacity for this given channel. Okay, so we already know that channel capacity of a channel is given by B times log base 2 1 plus S by n, right? And here B is actually equal to 3400 hertz, and this is times log base 2 1 plus 1000. So this is 1001. This value is going to be 1001, and log base 2, this value will be close to 10. This is approximately equal to 9.96. So we have 3400 times 9.96, which we will get, this will be equal to 33864. So this is the channel capacity of this channel in bits per second. Okay, is it clear? So now we have the second part as well here, and that basically says that for the same channel, if the transmission rate, we have to transmit at this rate 48000 bits per second, then what will be the minimum SNR needed? So now we have to calculate SNR when this is going to be our new capacity, and since it is the same channel, so bandwidth is going to remain same. So let's calculate that once again. So here you can see that again we have to apply the same formula. So our channel capacity now is our new channel capacity is so our channel capacity is 48000, and this is equal to B is same 3400 times log base 2 1 plus S by N. So we have to calculate this value, and you see that this we can say that log base 2 1 plus S by N is actually equal to 48000 divided by 3400, and this will be equal to 480 divided by 34, and you can say that 240 divided by 17. Okay, so this is log 2 1 plus S by N. From this equation we can actually calculate 1 plus S by N by simply taking 2 to the power 40 divided by 17. So that I'm going to leave it as an homework, so you can do this. Now we are going to move on to the next example that we have. And here in this next example, this is also a homework for you, so you have to solve this problem. This has also been asked in the university examination. Here it says that an ideal communication channel with average power limitation and wide Gaussian noise has a bandwidth of 1 megahertz. So B here is given as 1 megahertz 10 to the power 6 hertz, and SNR is equal to 10, and SNR is 10, right? So we have to calculate channel capacity. So C will be simply equal to 10 to the power 6 1 plus 10, log base 2 1 plus 10, and this is 11, so this will be 3.33 something, and 10 to the power 6. So you can see that 3.33 megabits per second. Okay, so this is going to be our channel capacity. Now the second part is, if an SNR drops to 5, calculate the bandwidth that is required for the same capacity. So capacity is going to be 3.33 megabits per second, and SNR will reduce to 5. So we have to somehow increase the bandwidth. So the new bandwidth we have to calculate. So this is the second problem. Okay, now let's move on to the third topic that we have to actually discuss here, and that is approximation of information capacity theorem. So there are two cases of approximation here. So very first case is that when SNR is very large. What I mean by that, S by N is much greater than 1. It is greater than 1. Then the logarithm can be approximated like this. So we have in the formula, channel capacity formula was C equal to B log base 2 1 plus S by N. So we are basically simplifying this log 2 1 plus S by N part. So you can see log 2 1 plus S by N can be, since S by N is much greater than 1, so 1 plus something that is much larger than 1 is approximately equal to that thing. So this can be approximated like this, and if I convert it to base 10, then it will be log 2 base 10 times as well, right? So this will be log base 2 base 10 will be 3.32 times log 10 S by N, right? And if I will simply multiply here 10, if I approximate it, I can write it like this, that this is 0.332 times 10 log S by N. I'm doing this so that I can, this value is basically in dB. Okay, so channel capacity will be this value times B. So this is going to be our new channel capacity. C is equal to 0.332 B SNR in dB. Is it clear? Okay. So now the next topic here is that next we are going to approximate is power limited case. So in this case, say that SNR is very small. It is much lesser than 1. So we can again approximate the same algorithm, that log base 2 1 plus s by n can be written as, I can convert it to base e. So this is log base e2, and then we have this value, right? And 1 plus s by n, and you can see that log 1 plus x can be actually written as x minus x square by 2 plus x cube by 3 minus x to the power 4 by 4, so on and so forth, right? So if x is very small, then this whole thing can be approximated to x only, because if x is much lesser than 1, then x square is absolutely going to be very small, right? So we can ignore those value and this value will be equal to x, right? So in that sense, if we apply the same approximation here, I will get log 1 plus s by n will be equal to s by n, where s by n is very smaller than 1, because this is the power limited case. So we have 1 upon log base 2e, log base e2 and s by n, and now the channel capacity C will be b times 1 upon log base e2 s by n, and this n can be, n is noise power, and this is actually written as noise power spectral density n times bandwidth, okay? Or it can also be written as, this is one-sided noise power spectral density. It can be also written as n by 2 times 2b, where n by 2 is the two-sided noise power spectral density. In any case, the value is eta times b, okay? So you can say this is eta times b, and if you simplify this, the value of C turns out to be 1.44 s by n. This is the maximum capacity that can be there, okay? For no matter what is the bandwidth, this is the maximum capacity of the channel, okay? So this is theoretical limit, you can't cross this. That's why it is also called as Shannon's limit. Shannon's limit. There has been quite a few problems that has been asked in the university examination as well as in GATE based on this formula and the previous approximation. So this is a very important formula and very important topic for GATE examination as well as for university examination. So thank you. If you have again, this is the same, we are plotting our channel capacity actually. C is equal to, so we are plotting C is equal to b log base 2 1 plus s by n, and s by actually eta naught. So we have taken s by eta naught to be equal to 1, so that value is constant. So this is basically channel capacity versus bandwidth, okay? So as you can see that till this point in this region, up to this region, you can see from here to here till this region, we are in the bandwidth limited regime, okay? And in this region, after that, this region is power limited regime. But no matter what is the value, you can see this is the theoretical limit of 1.44 s by eta naught, and you can see that it's always less than that. This is the maximum value that can be there. So this is one of the interpretation of channel capacity versus bandwidth, that this whole graph can be actually taken in two parts. One is bandwidth limited regime, another is power limited regime, okay? So thank you for tuning in. If you have any question, you can post that into the comment section. Thank you.